Good morning, everyone, and welcome to the first session of PyCon 2025 and the first talk of this session. We're going to start off with Alvaro from Kiwi.com, who in 30 minutes is going to walk us through building a NoGIL load balancer. So please give a warm welcome to Alvaro.
Yeah, thank you. Thank you so much. Okay, I've seen on the schedule that we're going to have lots of NoGIL talks today, and probably in the future it's a recurring theme that we're going to hear a lot about regarding Python. First things first, can you raise your hand if you've never heard about the idea of NoGIL free-threaded? Okay, I'm in the right audience. For those of you who raised your hand, you're probably punching a little bit up, but I'll try to keep things as approachable as possible. Feel free to reach out to me at the end of the talk if there's something that you didn't grab for whatever reason. Okay. For those of you who've heard about the NoGIL stuff, who thinks this is something that will make Python faster? Can you raise your hand? Okay, let's see. I think you've been lied to about. I don't know why. Have you noticed that the guy who was presenting free-threaded from Meta not even once said the word fast? And that didn't ring anything weird? Okay, we'll find out why that's anything to do with this. So first things first, this GIL is just something that we had on Python for a long time. It's been a barrier to the performance in multi-threaded programs. You know that you can run thread programs in Python, though you can only run one thread at a time. And though we have mechanism for concurrency, the GIL has exerted a powerful influence in the language, and many libraries assume single-threaded or are not memory safe when using multi-threads until now. So in 2021, Sam Gross from Meta introduced a proof of concept for a NoGIL Python, a Python that doesn't have the global interpreter lock. And that means that without that GIL, we're going to be able to run Python on different CPUs at the same time, making programs faster. Or so I was told. So first, I wanted to discuss a little bit what I mean by CPU bound and IO bound, because it's stuff that is going to be happening recurring during the talk. A task whose bottleneck is running the code is CPU bound, and a task whose bottleneck is waiting for the outside is IO bound. I know this is not very academic definitions, but at least we're going to go with that for now. In CPU bound tasks, the GIL is there to force threads to sometimes stop midway. In IO-bound tasks, the GIL allows tasks who are waiting for the IO to come through, like from data from a file or something like that, to stop voluntarily so that all the threads that need to run on the CPU might go along while the other thread is running, is waiting. We're going to build a load balancer, and I know that a few of them are like, why the hell has a load balancer has anything to do with threads, CPU, and stuff and all that? The thing is, a load balancer is just a server that acts as a single point of entry to multiple servers in the background, and it's relevant because it combines both types of tasks. On the one hand, you got that it's proxying the connection, which is a CPU bound, and waiting for each server to return the response that can be proxied back to the client, which is going to be an IO bound task. The interesting thing about this is that many software systems are designed in a somewhat similar manner. For example, you've got data processing like Spark or Hadoop. You also have AI pipelines. You have scientific simulations like BLAST or genome assemblers, and you have all the non-Python stuff, or at least the classical non-Python stuff, like video games, databases, video editing, stuff that for stuff for which Python has never been the first choice as a programming language. So if you're interested in try using Python for these exotic uses, maybe NoGIL is the way forward. We'll see about that. So what we'll do today is I'm going to first walk you through a threaded Fibonacci server, a server for which we're going to pass an integer, and we're going to receive the Fibonacci calculation of that number. We're going to stress test it, with special kind of tests that I'm going to walk you through as well. And we're going to remove the GIL from it with a free-threaded CPython build. And we're going to see what happens. Then I'm going to use a NoGIL load balancer, which in reality is just another server with a few modifications. And we're going to stress test it. And we're going to see what happens. After that, I'm going to switch from a very simple load balancer algorithm to something that is a bit more rusky and sophisticated called list connection. Some of you might know what I'm talking about. And finally, we're going to have a little bit of magic. All right, are you ready? Cool. If you're trying this at home or in the future or whatever you are with your computer right now, bear in mind that I'm going to be using 3.14, the beta version, which was released 10 days ago. Served us as a warning that it's not meant to be production code here, so don't be cheeky with PEP 8 and all that stuff, because I'm not following none of that in the presentation. And yeah, though I'm using 3.14, 3.13 will be valid version of Python. Previous version don't have the free-threaded build, so you won't be able to use that. And if you want to follow along, I've got a repository that you might be able to look at after the talk or during the talk. Feel free to go for it. So I'm not going to be diving too deep into what a socket server does, but this is the code exactly what is going to be happening. If you are familiar with networking programming, it's fine. If not, it's fine too. The idea is that we're going to have a code that accepts multiple connections. And though this code is valid, we're not going to be able to do it in the current form, because while the infinite loop is going to be able to loop through multiple connections at the same time, the fact that handle is a synchronous function means that it's going to block, which means that I'm going to be able to use this server only for one connection. And for that, threads are very handy. So the thing is that if I use a thread, then I just start it and move on with the next connection, which is going to be blocked at the sock accept level. Okay? So each time a new client comes in, the sock accept is going to return the socket and the address, and the new thread will be started. That's the gist of it. So how am I going to stress test this server? So I'm going to be using a code that is a bit inspired by a talk that they basically gave a few years ago. And the idea is that I'm going to be running a task that is going to be waiting for 1 second and print the number assigned per each client. That is going to be the numbers of requests per second. That's it. We're going to have a number of clients, each one assign an integer, and that integer is going to go up as new requests start and finish as we monitor them along. And how are we going to monitor each of that client? Well, we're going to create the socket on that connection, and we're just going to send one. Okay. The thing is, Fibonacci number, it's easy to calculate what the Fibonacci of 1 is. It's going to be immediate response from the server. And after that is received by the client socket, we're going to increment that that number by 1. And we're just going to loop through it as fast as we can so that we can see how many requests we have per second. And finally, we're going to have as many threads as we need per number of clients, and they're all going to be daemonic. Well, the main thread is going to be running this monitor for requests per second. Okay, so let's see what happens. So first, I want to show you that I'm not missing out with the version, and I'm going to be running this server. This server is going to be running at the port 8000, and what I'm going to do now is, on parallel, I'm going to be running this test on the same port, and it's going to be 3 clients. Okay, you can see that the clients are being established, and you can see that we have around 24,000, 25,000 requests per second for each server. So this is like, okay, this is a server, it's doing server 3 things, but I want to show you something that is going to be interesting. What if I create a new connection and I send something that is going to take a long while, like, I don't know, 38. Okay, notice that these connections that we have, they for whatever reason, they go down, okay? So something is preventing the other requests for running, and that is the GIL. So the GIL is there, it's screwing us. What is happening in reality is that the GIL is taking over the CPU that is running for Python. And that's essentially what's happening. So when we serve multiple requests when they are fast, the possibility that there's going to be a switch between one thread and another is very low. Like the GIL is very efficient in that switching between one thread or another. So you're not going to see much of that. Okay? The problem is that if you have a request that is very slow, it's going to take over the CPU. And unless the language decides to switch back to one of the smaller, more faster tasks, it's going to be running that long one. So it's going to prevent the others from running, and the number of requests per second is not going to go as high as on the other way. Something good to say, though, is that the threads are going to be suspended by the language and not by ourselves. And why do I say that? Well, because if we, for whatever reason, decide to try this with asyncio, which is something that I'm not going to do today, but if you try this, you're going to realize that if you decide to design these in a way that currencies are taking turns on a single thread, they're going to be suspended if there's a slow request. And being suspended, that means that it's going to be in the queue. And they're going to wait, and they're going to wait, and they're going to wait. So the number is not going to be low. It's going to be a big fat 0. Okay? So asyncio doesn't solve the problem that we have. So what happens if we remove the GIL? Okay, we'll see what happens. So, what I'm going to do is switch to the GIL. So let me first clear this stuff. The way I do it is this easy. So recall that I was switching to the normal version of Python here. So the free-threaded or no-GIL version is just adding a T to it. And that's it. I don't have to do anything else. There's no special configuration. That's it. Okay? I'm going to be running the same server. And I'm going to be running the same test. So first thing you might realize is that the throughput went up a lot, actually. So that's a good thing to have. That could mean that no-GIL is actually faster. So maybe we haven't been lied about, though. And what about the stuff that I was doing earlier? So nothing happening. This is great. Like the no-GIL is actually doing what it was promising to do, which is that it's running on multiple servers, and therefore, if I have a new task going on parallel, there's not going to be anything preventing those CPUs from keep running their own threads. So that means that we're not going to see a throughput hit, but we're going to see something weird, because if instead of having 3, I've had 6. We see a throughput hit. Okay, so you see that rather than having 33,000, 34,000, we now go back to 18, 17,000 per client. Like this shouldn't be happening, right? If we have multiple servers or multiple threads or multiple CPUs, like they should be independent, right? So something weird is happening here. So for that reason, we're going to try something that might have a little bit simpler, which is like having these load balancer in the middle. Yeah, like I said, the long-lived request problem disappears, but we have this that I call load sensitivity. Like the number of clients affects the throughput for each client. So we're going to build a load balancer to see if we can get rid of that, okay? So actually the load balancer code is pretty simple. Like imagine that we just copy pasted the code that we had in the load balancer. I'm just going to have to make a few tweaks here and there, and we're going to be able to get going. Okay, so the first thing that I'm going to do is add a new parameter, which are going to be the server ports, the list of ports on which we have the servers that this load server is going to be quote unquote responsible for. Okay, we're going to direct the requests that we have from the client onto the servers that are located on these ports. The thing that we have to do now is now that we receive the connection from the data from the client, we need to send it to the server that we want. And for that reason, we need to create another socket connection, and we're going to have to connect to that server port. And the thing that I'm going to do, just for simplification, is just assign a random one. Okay, I have a list. I'm just going to assign a random of choice of it, and that's going to be it. Literally, it's going to be it. Because now, on the code that was calculating the Fibonacci number and returning the number to the client, what I'm going to do is just proxy what is coming into the server, and whatever is the response, I'm just going to proxy it back to the client, as any load balancer is meant to do. And just finally, just make sure that the load balancer has the information that's correct, which includes the number of server ports, and yeah, just for clarification, the small trick just turns the strings that are coming from the script into numbers, nothing to be worried about. And we're going to create for each port in the server port, we're going to create a thread, a demonic thread that is going to be running for those servers on the background as the load balancer is going. Okay, so let's test it. It's going to be running on port 8000, 8001, 8002, 8003, and we should have everything, okay? So we have 3 connections, and why are we having these low numbers? We should have, isn't this confusing? Like, we should have a high number. Like, maybe not the 34 that we have in the beginning, but why not? Like, we're having half of that. We only have added, the only thing that we have added that's new is that random stuff. Turns out random isn't memory safe. Okay, and the thing about the random not being memory safe is that there's a hidden fine-grained lock that the language has put in place so that it's memory safe for the language. I'm not entirely sure why this is happening. My best guess is that the seed of the random library isn't memory saved as Python is currently written, but this is just a best guess, okay? So they wrapped around the whole thing inside a fine-grained lock so that the random is memory safe in the NoGIL environment. How might I be able to prove this? Well, what I'm going to do is switch to a different load balancer, okay? This load balancer in the new configuration is going to be something called least connection. And the name is what it's meant to be. We have different services, and we can count the number of active connections that we have per each server. And each time a new request comes along, we're going to decide to give it to the server who has the least number of connections at that moment. Okay, we're going to keep the balance not just randomly, but rather we're going to select the servers that are the least active, the least busy, and try to balance it out in a dynamic way rather than just keep things random. Okay. Doing this is actually pretty simple from what we have. And the thing is that this is relevant, not just because we want to prove that random is actually using a fine-grained lock, but actually because least connection relies on a single source of truth to store and receive that number of connections. We're gonna need a single source of truth for that. And that shared mutable state, which is something that threads are very good at compared to, for example, processors. If you try to do this, it's probably going to be not just harder, but actually less performant. Again, something that I'm not going to do in this talk, but you can try it yourself. it's actually harder. And the fact that you have to serialize data to communicate between each processor means that the throughput is going to be impacted by that added complexity and added time to send this message across. But in order to use this shared mutable state, we're going to have to add a threading lock. Okay, it's going to be a mini version of the GIL, but that's actually going to make explicit what random is actually hiding from us. And this lock will ensure that only one thread is reading or writing into that sort of truth at one time. So what I'm going to do that for now is that rather than passing the server ports to the handle, we're going to pass a router object. And that router object is going to implement two methods. One is going to acquire the port, for which we're going to use the server port that we're going to pass on to the connect method that we were passing the random choice before. And the second thing that we have to do is that on the client losing the connection or closing the connection, what we're going to do is release that port, which is going to be the second method that we have to do. And yeah, this class is pretty simple though. The instantiation of the class is just going to have two variables, which is on the one hand, the threading log that I was referring about, and on the second is just a simple dictionary on which each port is going to be the key and the number of connections is going to be 0, okay? The acquiring port, what it's going to do is engage the log, acquire the log, so that no other thread is running this code at once. So only this thread is going to acquire these, and it's going to prevent any type of contention with the rest of the threads. And we're going to calculate that port that has the least connections. Okay, it's going to calculate the min of all the ports, which are the keys of that dictionary, ordered by the number that is the value on each dictionary. Hopefully this makes sense. It's a bit tricky, but yeah. Raise your hand, this makes sense? Okay, cool, amazing. I was not sure. And yeah, afterwards, they're just like adding one to the port of actives, and that's it. And yeah, the releasing is even simpler. We just grab the lock, make sure that no other thread is doing anything weird, and we just decrease it by 1. That's it. So let's see what happens. So bear in mind, what we're going to do now, just to repeat that, is rather than using the load balancer that is random, we're going to do the list connection. But the thing is going to stay the same, okay? Same number of servers, same number of ports. And we're going to see that if I do the same test, we do have the same number. So once I remove the random and I add this list connection, I get the same number, which is like explicit, or at least there's some sort of down-to-earth proof that random is actually having some sort of fine-grained locked that is preventing this from going up. That said, I haven't solved the problem of what the hell is going on here. I should get like a higher number, right? And yeah, the reason this isn't happening the way it should is that I've been talking a little bit about the CPU bound and IO bound, and the fact that I'm doing requests that are very rapid, very fast, means that the dominant effect of each request is actually the waiting for the connection, not the CPU that it takes to run the Fibonacci calculations. So I might be able to tweak the test and see what happens, okay? So what if instead of sending 1, I send a higher number, like 30. Same thing, okay? Obviously, the number is going to be lower because the task is going to run for longer. But the question is, what happens if instead of 3, I use 6? The number doesn't change. The number doesn't change. So here's something tricky that's going on, is that the moment that I engage more CPU into the task itself, rather than just making the request be wait for the answer and back, the IO becomes less of the dominant term of the whole process, okay? So this task is less IO bound and more CPU bound, okay? Why is that important? Well, because if I'm engaging more with the CPU, the GIL is going to become a problem, a bottleneck in this case, okay? The moment that I have multiple CPU cores at my disposal, I'm going to be able to run these slower tasks on different CPUs that are going to run independently. And that means that the number of connections is going to be independent per client. Hopefully this makes sense, okay? So let me try explain it again. If I have a task that is all about waiting for the connection to come back, and not CPU, not run stuff on the program, on the laptop, then the no-GIL isn't much of a difference, isn't much of an improvement, because the GIL is actually prepared and ready to do this kind of waiting for the other thread to come along. And it's very efficient at doing that. Like, we've been decades into the Python language, and the GIL is very, very, very efficient at waiting for different tasks at the proper times. But the no-GIL isn't. But that said is that if I have tasks that require CPU, that require a bit of complexity on the CPU rather than just waiting for stuff to happen, then the no-GIL is great because we're going to have multiple things happening on multiple CPUs. Let me show you why. What if I, instead of using 6, I use a higher number, which is like 10? Okay. This is stuff that doesn't happen every time, but hopefully this, yeah, okay. Do you notice that from time to time, I have a 6? It usually gets amplified a few times, and especially if I start running numbers that are actually quite big. Like, I have 5s, I have 6, I have 7s, I no longer have the 8s that I had before. The reason is that I'm using a higher number of threads. And the fact that I'm using 11, 10 means that I'm using a number that is higher than the number of CPU cores that I have on my computer. And that's the part where the no-GIL is no longer effective, okay? I no longer have more CPUs to run things in parallel. So I'm gonna start to have to reuse some of that CPUs again, which means that I'm gonna re-emulate the behavior that used to be on the GIL. And just so that we can see the whole thing with the GIL again, let me show you. If I go back to 3, they all go around 6, 9, 7, and no matter how many threads I do, the count is always around that 6, 8, 7, 8, 9, okay? So the thread is switching, but only is running 1. So that means that the number is always going to add up to 8 by virtue of the GIL preventing all the threads from running at the same time. And yeah, just 1 is going to be 8, obviously. So let me wrap this up real quick because I only have 2 minutes left. When I/O dominates, again, when we have fast requests that don't engage the CPU too much, the GIL has better throughput per client. But when CPU dominates, like when we have requests that are slower, the no-GIL scales better. Like, we can have multiple threads running independently, and we're going to have more. We're going to have the computer engage more, and it's going to run more efficiently. The load sensitivity disappears for no-GIL with less than 8 clients, which in my case considers with the number of CPU cores. If your computer has a different number, it's probably going to be having a different result, but like similar in the spirit. And having CPUs switch from one task to another, like when we move beyond that number 8 in my case, we're going to have a GIL-like behavior, even if we run with a no-GIL Python. So yeah, I think now is your time. I think I've talked enough, right? GIL is faster for single-threaded programs. NoGIL scales better for multi-threaded programs. Unexpected bottlenecks, like having random, lurk in the language. Like there's stuff that isn't memory safe in Python. Deal with it. And yeah, finally, give it a go. NoGIL Python is experimental. That means that it doesn't bite. It's up to you to grab it. Enjoy the conference.